In this video, I will provide an introduction to quasi-experimental designs, and I will discuss Rubin's causal model, which we'll use to understand quasi-experimental designs. I will first talk about experimental designs to provide a context. The objective of experimental designs is to estimate the effect of a treatment or a program intervention outcomes. And the main characteristic of it is that participants are randomly assigned to conditions. That is an absolute requirement of experimental designs. But they don't need to be randomly sampled. You can, for example, do an experimental design with undergraduate students that sign up because you posted a flyer. So random sampling does not affect the validity of experimental designs as long as it's randomly assigned, as long as participants are randomly assigned to conditions. Now, conditions are also manipulated. In other words, the experience that participants have in each of the groups is defined by the researcher. Quasi-experimental designs, by contrast, are interested in evaluating the effect of a condition, but there is no random assignment. Therefore, individuals are not assigned randomly to treatment and control conditions. The most common situation is that individuals self-select to participate in the treatment or control condition. So, for example, you could have a study of a training program where individuals decide whether they will join the training program or not. Manipulation of conditions may be possible. As a researcher, you may have control of the experience that participants have in the training program, or you may not have control. The control may be with someone else and you just receive the data. What's different between a quasi-experimental design and correlation studies is that for a design to be quasi-experimental, there needs to be baseline equivalence between treatment and control group. Now, in experimental designs, baseline equivalence is achieved with random assignment. In quasi-experimental designs, baseline equivalence is achieved by means other than random assignment, such as matching participants, weighting participants. The objective of baseline equivalence is to make sure that participants in treatment and control groups have similar distributions or important covariates, such as the pretest. If there is no baseline equivalence in the study, then it's not a quasi-experimental design, it is just a correlational study. So here's an example. A study to estimate the effect of high school student participation on a career academy on future income. The treatment here is Career Academy, which is a high school program that integrate academic preparation and workplace experiences. So in this situation, you cannot random assign individuals to participate in a career academy. Individuals self-select to either participate or not. So you can get secondary data. So, for example, the educational longitudinal study has data on whether individual students participated in a career academy, and also has outcome data such as their future salary. So the research question here is, does participating in a career academy in high school affect future income? Typically, if you were getting data from a national survey, you also have to be aware and account for the complex sampling scheme that's used in national surveys. In this case of the educational longitudinal study, it's a two-stage stratified sampling method where schools were sampled with probability proportional to size, oversampling Asian and Hispanics. What it means is that in order to account for this sampling design, you will have to use sampling weights. and you have to estimate standard errors in ways that are compatible with the fact that students are within clusters, which here are schools. So, for example, you could use cluster robust standard errors, or you could do a design effect adjustment to clustering. Now, here the treatment comes from a question that asks whether students were in a career academy, and 8.5% of the students participated. So this is a typical situation that it would be could be a quasi-experimental study if, as part of the analysis, the researcher succeeds in obtaining baseline equivalence between students that participated in the career academy and students that didn't. Right? If so, baseline equivalence on relevant covariates. If baseline equivalence cannot be achieved, then the study would just be a correlational study. Okay, so in terms of internal validity is the ability of the study to provide information about causal relationship between treatment and outcome. So internal validity is the strongest in experimental designs, because experimental designs control for sources of selection through random assignment, because there is random assignment, there is no selection bias. Now, for non-experimental designs, there could be many factors that are related to the participants selecting the treatment and also related to the outcome. And in quasi-experimental designs, by demonstrating that there is baseline equivalence, you provide the evidence of internal validity. Obviously, it also assumes that there are no omitted covariates. In other words, the covariates that you are demonstrating baseline equivalence on are the only covariates that are confounders, and you haven't omitted any. So no omitted confounders is an assumption here. So talking about confounding variables, what's a confounding variable? So a confounding variable will lead to bias if ignored in the analysis of data from quasi-experimental design. Now, true confounder is a variable that's related to the probability of treatment and to the outcome. So, for example, in the example where the treatment is participation in a career academy and the outcome is future income of participants, it could be that parent socioeconomic status is a true confounder because it relates to the probability of individuals joining a career academy and also relates to the individual's future income. So a variable that is only predicts the treatment but is not related to the outcome is not a true confounder. Also, you can have an outcome predictor that only relates to the outcome but not to the probability of treatment. And those variables, ignoring those variables does not cause bias. Okay. Now, there could be a mediator too, which is a variable that is caused by the treatment and has an effect on the outcome. You could study those variables with a mediator analysis, but most importantly, you should not control for a mediator, because if you are, you're essentially removing part of the treatment effect. Okay, so here are some examples of potential confounders for the career academy study. So parents' high level of education, home literacy resources, number of academic risk factors, the students' response about how far the school they think they will get, parental expectation of success, urbanicity, geographic region of school. The last two, noted that the last two are not individual level confounders, they are school level confounders. If you are working with data that's nested. So in this case, students are within schools, you have to be aware that there could be confounders at the cluster level, which in this case are school level. Okay, when thinking about quasi-experimental designs, and propensity score analysis in particular, it's helpful to discuss with the Ruby's causal model, which is also known as the potential outcomes framework. So in Ruby's causal model, all individuals in the population have potential outcomes in the presence and absence of treatment. Okay. However, you can only observe one of those potential outcomes. So for the treatment group, you only observe the outcome in the presence of treatment, and for the control group, you only observe the outcome in the absence of treatment. So here you can see a matrix of potential outcomes. For participants, you have the potential outcome in the presence of treatment. For Z, Z is the treatment indicator for those that are treated. So Z equals 1 indicates that the person was treated. And then here you have the potential outcome in the absence of treatment for those that are treated. Now this potential outcome is missing. It's not observed. Similarly, we have for non-participants, we have the potential outcome in the presence of treatment for those that are not treated, and this potential outcome is missing. And we have the potential outcome in the absence of treatment for those that are not treated. This potential outcome is observed. So it's essentially a missing data problem where the diagonal here is observed, the off diagonal is not observed. Now, based on Ruby's causal model, you can define an individual treatment effect, which is for each individual is the difference between the outcome in the presence and the outcome in the absence of treatment. Now, this cannot be estimated directly because for every participant, one of these two potential outcomes will be missing. Now, the average treatment effect then is the difference between the expected value, which is the mean, of the outcomes of the individuals in the two treatment conditions. So here we have the expected value in the presence of treatment and the expected value in the absence of treatment, and the ATE is the difference between these two respective values. Now, we typically estimate, like the conventional estimation of ATE, ignoring selection bias, would be just the sample mean of the treatment group minus the sample mean of the control group. Now, this estimator is valid, is unbiased for an experimental design. Now, why is it unbiased in experimental design? It's because the control group is a valid representation of the treatment group if the treatment group had not been treated. Okay, so more specifically, in an experimental design, the expected value of the treated outcome in the presence of treatment is equal to the expected value of the treatment outcome in the absence of treatment for those that are not treated, right? So in other words, those that are treated are equivalent to those that are not treated if they had received the treatment, right? And similarly, the expected value in the absence of treatment for those that are not treated, which is the control group, is equivalent to the expected value, is equal to the expected value in the absence of treatment for those that are treated. In other words, the control group is equivalent to the treatment group if the treatment group had not received the treatment, right? And that is true in experimental designs due to the randomization, which means that this estimator here is unbiased. Now, but for a valid treatment effect estimate, there is a bigger set of assumptions that need to be true, and some of these are can be achieved by random assignment, others cannot. That means you need more than just random assignment to achieve them, and I will go through. So strong ignorability for treatment assignment is saying that the treatment assignment is independent of potential outcomes distributions given observed covariates, right? So here we have the two potential outcomes: y in the presence of treatment and y is absence of treatment, is independent of whether individuals were treated or not. Okay, given covariates, right? So if you this for the treatment assignment, for an experimental design, this is true regardless of covariates because randomization guarantees that. Now, for quasi-experimental designs, if you are controlling for the right covariates, you can achieve strong inability treatment assignment, conditional covariates. Now, related to that assumption, we have the assumption of overlap and positivity, which requires that the probability is not zero. The probability of treatment assignment is not 0 or 1. In other words, no participant should be guaranteed to receive the treatment or not to receive the treatment. They have to be. They have to have a probability strictly between 0 and 1. Now, the stable unit of treatment value assumption is an assumption that there is a unique potential outcome for each treatment version. Okay, so each treatment version has only one potential outcome. So the implication of that is that the potential outcome of one individual is independent of the status of another individual, and there is no unrepresented versions of the treatment. So let me exemplify this in the context of spillover effects, which results in violations of Sutiva. So let's say there is a student in an elementary school that's receiving a treatment that's a tutoring, a one-to-one tutoring after school. And there is another individual, another student that's not receiving tutoring. So it's the control group. So for Sutiva to be valid, right, the potential outcome should be independent of whether they are treated or not. But let's say that one of the students in the treatment group does homework with his neighbor who happens to be in the control group. In that case, you are creating an unrepresented version of the treatment, which is, not receiving tutoring, but doing homework with someone who received tutoring. So you see, it's like you don't have two treatments anymore, tutoring and not tutoring. You have an extra treatment, which is not tutoring plus homework with someone who was tutored. And therefore, there is an additional potential outcome, which is the potential outcome for not treated, but doing homework with someone that treated. And that potential outcome is dependent of the fact that the neighbor of that person is treated, right? So you can see it's a clear violation of Sutiva because it creates a third potential outcome that's from an unobserved version of the treatment, and that is, a student in the treatment group doing homework with someone in the control group, is a spillover effect. Okay, so that's an example of violation of sutra. Now, non-compliance is, let's say, the someone a student is assigned to tutoring, but the student skips several sessions of tutoring. Um, Again, creates multiple versions of treatment because now you have, full tutoring, you know, attended 80% of sessions of tutoring, attended 50% of sessions of tutoring. You can have many different versions of the treatment. It's still valid to estimate the ATE for the effect of offering tutoring, regardless of compliance. This is known as estimating the intention to treat effect, which ITT. It is still valid. It's very helpful, for example, in public policy. What's the effect of offering vouchers to students, regardless of whether they take voucher? What is the effect of offering a vaccine to a population, regardless of how much of compliance with vaccination program that is? Right. So it can be very important to understand to estimate the ITT effect, and but which is different. Like if you really want to know the effect for those who complied, you'll be estimating something called CASE, complier average causal effect, which I'm not going to discuss here, but it's important to be aware that the complier average causal effect is different, potentially different than the intention to treat effect when there is no compliance. You can also have attrition. So an assumption when you're doing quasi-experimental design is when there is no attrition for the post-treatment. That generates missing data, and it can have a mechanism that's not random. In other words, the reasons for attrition may be related to the outcome, so you are losing part of the outcome that is for a specific group that's different than those that stay in the study. It's possible to model the mechanism of attrition if there is information about it, but it's you need to make strong assumptions about the nature of attrition to be able to control for it. For example, it's possible to create weights to try to remove attrition bias, but again, you need to model the mechanism of attrition. So the average treatment effect for the treated is another estimate you can obtain from a quasi-experimental design. Now, it's different than the average treatment effect because it only generalizes to the treatment group. So it's the difference between the expected value of the outcome for those that are treated and the expected value for the untreated outcome for those that are treated. Right. So it's answering like what is the treatment effect only for those that are treated. Now in quasi-experimental design, because the treated group and the control group are exchangeable, the ATE and the ATT are the same, but it's not true in quasi-experimental designs. It may be that those that choose to be treated will have a higher effect than those that choose not to be treated. Okay. Conversely, you could also potentially estimate the average treatment effect for the control, which is the difference between the expected value for the treated outcome for those that are not treated and the expected value of the control outcome for those that are not treated. So this answers the question, what's the effect for those that were not treated if they had chosen to be treated? Typically not of much interest, but it's you can estimate it with methods such as propensity score analysis.